The concept of equilibrium means the net force is zero. Net force equals zero. That would apply to a case where something is stationary and has several forces on it, and if it's going to remain stationary, the net force would have to be zero. It also applies to the case of an object moving at a steady speed and not changing direction. In that case, the acceleration is zero, so therefore the net force would be zero. So let's do an example. Alright, we have two forces acting on this, F1 with a magnitude of 12 newtons acting at an angle of 35 degrees, and F2 with a magnitude of 38 newtons acting at an angle of 135 degrees. So the challenge is to find F3 for equilibrium. So for equilibrium, we know that the net force will have to be equal to zero. And that means that F1 plus F2 plus F3 equals zero. Which means that F1x plus F2x plus F3x has to be zero, and F1y plus F2y plus F3y equals zero. So that's our strategy. We're going to find the components and plug them into these equations and look for F3x and F3y, and those will be the components of F3. So these are the components of F1x and F1y. F1x is F1 cosine of theta, and that comes out to 9.83. F1y is F1 sine of theta, and that comes out to 6.88. And F2x is F2 cosine of theta, I should say theta 2, and that comes out to negative 26.9. And F2y is F2 sine of theta 2, and that comes out to 26.9. So now we put numbers into the equation F1 plus F2 plus F3 equals 0. And we're going to handle that with the x components and the y components. Okay, with the x components, we plug in the numbers, and we get that F3x is 17.0. For the y components, we plug in the numbers, and we get that F3y is negative 33.8. So this gives us our x and y components of F3. Now, to get the magnitude and direction of F3, we just say F3 equals the square root of the sum of the squares of the components of F3. And the angle is the inverse tangent of F3y over F3x. And we get 37.8 newtons and negative 63.2 degrees. So let's see if that makes sense. The magnitude was sort of about the same size as this vector, and the angle was at negative 63.2 degrees. So that's going to be somewhere kind of like this. It's not going to be directly opposite this. This is really 45 degrees from the horizontal. And we're looking at an angle here of a little bit more than that, so something like this. So that would be our F3. And if I drew F1 a little more accurately, it would be a little bit shorter and a little bit further down. It's less than a third of F2. So maybe even a little bit less. Alright, so if you consider F1 and F2, does F3 look like it would balance those? More or less, yes, according to this drawing. And if we draw the vectors out head to toe, we get F1 here, F2 like here, and F3 would be going like this. So maybe that one gives us a better idea of F3 and how it fits into the others. So that's the answer. So that we found F3 so that this whole system can be in equilibrium. Alright, in this example we have an object that's suspended by two wires with different angles. So that might be the case of like a traffic light or a chandelier hanging from the ceiling. So without saying so, the object is obviously in equilibrium because it's not moving anywhere. So it's implied that it's in equilibrium. So all the forces acting on it are going to add up to 0. So the challenge is to find the tension in the wires. The tension in the wires, when a wire has a tension, it has a tension on either end of the wire, like that. So that's kind of how tension is drawn. Tension is the force pulling on whatever the wire is attached to. And then the other wire is going to have a tension going like that. Since we're concerned with what's happening right here, we can ignore these tensions. Of course they exist, but I'm not going to draw them because we're really just going to focus on this point here. But the tension on one side of the wire is the same as the tension on the other side. So it's not like we're ignoring some information. we know that, like, if that turns out to be 100 newtons, we know that there's a force here of 100 newtons as well. Okay, so we're focusing on these tensions. Let's label them T1 and T2. Those are the tensions of the wire pulling on this point here. And then what else do we have? We also have mg here. So 50 times 9.8. We have gravity pulling down. So those are the forces involved. And let's see what we can do. We have to have F net equals 0. That's really the key to the problem here. Which means that the F net x is 0 and F net y is 0. Alright, what we're going to need to do is find the components of those two forces. So T1 has a T1x and a T1y, and T2 has a T2x and a T2y. And by geometry, we can see that this angle is going to be the same as the angle here. So this one is going to be 18 degrees, and over here we're going to have 40 degrees. So let's write out expressions for all the components. Even though we don't have T1 and T2, we're going to try to find that. But we can still write expressions for the components and then put it into these two equations. So our expressions would look like this. T1x is T1 cosine of theta 1. So that's right here. So that's going to be just T1 cosine of 18. Now you could calculate that and have a decimal if you want, or you could save the calculation till the end. But that's as far as we can go. T1 cosine of 18, that's the best we can do for T1x at this time. T1y comes out to T1 sine of 18. T2x is T2 cosine of 40, and T2y is T2 sine of 40. Now these are just the magnitudes of those components. We're going to deal with the fact that they point, some of them point to the left, and what directions they're pointing in when we put them into the equation here. So now let's apply the first equation, F net x equals 0. So what is the net force in the x direction? Well, what do we have? This is all in the y direction, so that's nothing. Here is a force in the x direction, and there's a force in the x direction. So we have T2x pointing to the right and T1x pointing to the left. So that's going to be T2x minus T1x equals 0. So we can put in values. T2 cosine of 40, and if I add that to the other side, equals T1 cosine of 18. Alright, so that's one equation. Notice that has two unknown variables, T2 and T1. Now the next equation up here is F net y equals 0. So what are the forces in the y direction? We have T1y going up, T2y going up, and 50 times 9.8 going down. So T1y plus T2y minus 50 times 9.8. If it's going down, it's negative. If it's going to the left, it's negative. And the other ones are positive. Alright, so T1y is T1 sine of 18. T2y is T2 sine of 40. And then we have minus 50 times 9.8 equals 0. So we have another equation with two unknown variables, T1 and T2. So the way we solve these two equations, we have this equation and that equation, we have to solve them together. The strategy will be to solve one equation for one variable, plug it into the other, and then solve for the other variable. So let's solve this equation for T2. So T2 equals T1 cosine of 18 divided by cosine of 40. Alright, now we're going to plug T2 in. We're going to plug all of this in for T2 for right there. So rewriting this equation, T1 sine of 18 plus T2 is all this, T1 cosine of 18 over cosine of 40, and then don't forget this, sine of 40. Okay, so all of this was T2, just from right here. and then minus, or I'll say equals, 50 times 9.8. Now we have one equation with one variable, t1. So the way to solve that, we would factor out the t1. So now we have t1 times sine of 18 plus cosine of 18 sine of 40 all over cosine of 40. Now if you prefer to work with the decimals, at each point you can just calculate that and find the decimal. Or if you prefer to do all the calculations at the end, that's fine too. Equals 50 times 9.8. The way to solve this would be, basically it's 50 times 9.8 divided by all this. Would be T1. So, what do we get? T1 equals 442.6 newtons. And then we can find T2 by plugging that into here. So it's T2 equals T1, so 442.6 times cosine of 18 divided by cosine of 40, and we get 549.5 newtons. So these are our answers for the tensions. So now we found the tensions in the wires for this thing to be in equilibrium. And here's one for you to do. We have an angle of 28 degrees and 37 degrees, and the mass here is 76.2 kilograms. So you want to find the tension in the wires so that this is in equilibrium. The results you should get would be T1 is 658 and T2 is 728. And that is assuming that T1 is on the left, so T1 is pointing up like that, and T2 is pointing up like that.